All right, well, I apologize for that. Let's continue on here with our last example. Again, we're trying to do the same thing we did last time. We would like to find all of the absolute extreme values of, and this time our function is h of x, on the interval negative 27 to 27. So I might start by thinking about the domain. I know I'm going to need to find critical points, and if I have critical points, I need to make sure that those are in the domain of my function. So I'm just going to look at the domain of h of x first, just to determine if we're going to have any issues. I'm going to look at x to the 1/3 first, and remember that x to the 1/3 power is really just the cubed root of x. And this function, the cubed root of x, has a domain of negative infinity to positive infinity. So x to the 1/3, that's not going to give me any problems. X plus 4, that's a polynomial. That's just the equation of a line. You could graph that fairly easily here. Since it's a polynomial, it's a line. It also has domain of negative infinity to positive infinity, so that means that the domain of h of x is negative infinity to positive infinity, which means we shouldn't have any restrictions on our critical numbers when we find those. So speaking of critical numbers, let's go and find those. I need to first of all take the derivative of h of x. So I'm going to just rewrite my function here. H of x equals x to the 1/3 times x plus 4. So it's up to you how you want to go about this. You could, as it's written, take the derivative right now, but you would be using the product rule. I think I would actually just take this x to the 1/3 and distribute that through. This really says x to the 4/3 power plus 4x to the 1/3. And I can just take the derivative of this using only my power rule, which I always think is a little bit easier than using the product rule, or quotient rule, or things like that. So I'm going to take the derivative, h prime of x, derivative of x to the 4/3. I should have 4/3 x to the 1/3 power. Plus over here, 4 times 1/3, I'm actually going to have the same thing, 4/3 times x. This time I'll subtract 1 from my power. I should have to the negative 2/3 power. And I'm going to rewrite that with a positive exponent just because I know I'm going to be working with it a lot algebraically going forward. Let's say this. Let's say this is 4x to the 1/3 divided by 3 plus 4 over 3x to the 2/3 power here. And again, I think it's easiest to find your critical numbers when we have just that single fraction. Here we've got 2 yet again. I would find a common denominator between this term and this term. So the way we would do that, it's not too terribly difficult. I'm going to multiply this by x to the 2/3 over x to the 2/3. Oops. So let's see. My derivative, h prime of x, should look like 4x. When I take x to the 2/3 times x to the 1/3, I would add those powers together. 2/3 plus 1/3 would be 3 over 3, or just 1. So 4x divided by 3x to the 2/3 power, plus over here, 4 over 3x to the 2/3 power, which then I can write as a single fraction as 4x plus 4 divided by 3x to the 2/3 power. So here is my derivative. I think this is going to be the easiest version of my derivative to work with, because remember, I still need to find my critical numbers. That's why I found the derivative. So I want to find places, first of all, where h prime of x is equal to 0. So we said last time, hey, this rational function, essentially just this fraction, is only 0 if the numerator is equal to 0. So I'm just going to take my numerator, which is 4x plus 4, and set that equal to 0. Well, I have this equation I can solve. I'll subtract 4, gives 4x equals negative 4, so x must be negative 1. I know this is in the domain because we said the domain was negative infinity to positive infinity, but you will also want to check and make sure, hey, is that x value in the closed interval that we're working on? So here we're working with negative 27 to positive 27. Well, yeah, negative 1 lies between those two numbers, so we are good to go. Here is a critical number. But that's not the only way I can find critical numbers. I also need to think about places where h prime of x is undefined or places where it does not exist. And for that, again, I'm looking at this derivative right here, and I'm concerned, well, what if my denominator is equal to 0? What happens then? Then I'm dividing by 0. So I'm going to take the denominator, 3x to the 2/3 power is equal to 0. Dividing by 3 gives x to the 2/3 is equal to 0. And if I wanted to solve this equation, I would actually have to raise each side to the 3/2 power. But 0 to any finite power here will just be still 0, so I have x equals 0. Again, the domain we said negative infinity to positive infinity, that's not going to be a problem. 0 also lies in our interval of negative 27 to positive 27, so it looks like we're all good to go. We have our two critical numbers, negative 1 and 0. So next, I need to take the critical numbers that I found along with the endpoints of my interval and plug those into my original function. So I'm going to take negative 1, 0, negative 27, and positive 27, plug those into my function h of x. And you can work with the factored form that they gave us. So they gave us x to the 1/3 times x plus 4. This might be a little bit easier. Or if you wanted to use x to the 4/3 power plus 4x to the 1/3, that would also work as well. You should get the same answer regardless of which version or which version of the function that we're going to be working with here. So let's start with our critical numbers. Let's work with h of negative 1. I'm going to use this factored form just because I think that's a little bit nicer to work with when evaluating. This says negative 1 to the 1/3 power times negative 1 plus 4. And when I take that and plug that in, I get a negative 3. And then I also want to take 0, plug that in, h of 0. This is 0 to the 1/3 power times 0 plus 4. Here I should end up with 0. But I don't just want to take these 2 points. Remember, our interval, we said, was negative 27 to positive 27. We were working on this interval of negative 27 to positive 27. So I want to take these two x values as well and plug those into our function. So I want to take negative 27 and say, well, this is negative 27 to the 1/3 power times negative 27 plus 4. Here, this time, I should get, let's see, a y value of 69. And then I will take positive 27, plug that in here, 27 to the 1/3 power times 27 plus 4. And this time I end up with a y value of 93. So I've evaluated my function at my critical points and at my endpoints. The very last thing we need to do is just pick out what's the highest and what's the lowest y value. So our absolute max, our highest y value was 93. So we'll say our absolute maximum is at h of 27 equals 93. And our lowest y value was negative 3. So our absolute minimum is h of negative 1 is equal to negative 3. Remember that when we talk about absolute extrema, really it's the y value that we want to get across. So this is the important parts. That is the absolute extreme value, is always referring to the y value. One other word of warning I'll just mention here on these problems is we are now doing some work with the derivative h prime of x, and we're working with the original function h of x. Just be careful that you're working with the correct function. We're going to be doing this a lot going forward, where we work with both the original function and its derivative, and then eventually also we'll be adding in the second derivative as well. So just please be careful. Please be mindful of which function tells you what, and I'll be sure to really emphasize what function we're talking about in the sections coming forward, where we're going to be working with the original function, the first derivative, and the second derivative.